This video is a final run-through of all of the topics that could be assessed in the 2024 Physics Paper 1 for AQA GCSE Combined Science. I obviously haven't covered these in a huge amount of detail because I'm trying to keep the video to under an hour, but all of the topics in the specification are covered. Before we get into the physics content, a few last-minute reminders for your exams. Firstly, it's really important that you write in black pen and that you keep your answers inside the box on the exam paper, because your exam paper is going to be scanned. So if you're writing in a different colour or if you're going outside that box, then there's a chance that your work won't be seen and the examiner won't be able to give you credit for it. For all of your calculations, it's really important that you're using the SI units. Watch out for sneaky questions where the exam board may have made it slightly trickier by, say, giving you a mass in grams instead of kilograms, and then you needing to convert it. For all of the extended response questions, it's a good idea to be answering in the form of bullet points, because there aren't any marks at all for answering in full sentences in GCSE Science, and by giving your answer in bullet points, it makes it clearer to the examiner where you've put the marks, and also it's just going to save you a little bit of time. Anywhere that you see the command word evaluate, you need to give both sides of the question. So offer some comparison and try to add value. If you've been given a table with some data, don't just quote values. Also, it's really important that you write a conclusion. All of the evaluate questions in AQA GCSE Science have one common mark scheme, and without giving a strongly justified conclusion, you can't get into that level 3 where you score 5 or 6 marks. If you have to write a method, say for one of the required practicals, then make sure there's a logical flow to it. A really good way of doing this is to give your answer in the form of a numbered list of instructions. And then if you realise you've written things in slightly the wrong order, you can just change the numbers. That makes it really clear what you're doing. Also, have a read through at the end and say, will this actually make sense? If you gave this method to a little year 7 who'd never heard of this practical before, would they be able to follow it and collect the data that would allow them to answer the question? There are a lot of working scientifically skills assessed in all of your science papers. So these are things like identifying the 3 different kinds of variable, knowing the difference between something being repeatable, which is where you do it again using the exact same method and you still see the same pattern, or reproducible, where another group of scientists does the experiment or possibly uses a different method and they still see the same pattern. You should know that when you're looking at your equipment, the resolution is the smallest difference in results that you can identify. You should know that computerized methods like digital thermometers are more accurate, rapid and sensitive, and you should also be aware that if you're asked to draw a graph, then your line of best fit does not need to be a straight line. I know that the maths department keep telling you that it does, but for GCSE maths that's true, and for GCSE science and the rest of the real world, if your data curves, your line of best fit should curve too. All measurements contain error, which basically means that not every single measurement that you make is identical. There are 2 main kinds of error. There are systematic errors, which are caused by poorly calibrated equipment. This could be things like having a balance where the mass is always reading half a kilo lighter than it should be. So if you know that, then you can just solve this by always adding half a kilo onto your calculations. If this affects the balance when it has nothing on it and it's still saying minus 0.5 kilograms, then this is called a zero error. The other type of error is a random error, which could be caused because your equipment isn't sufficiently precise or just because of natural fluctuation in the true value of that quantity. So say if you're measuring the temperature of a room, that temperature might change over time. The way that we take account of this is that we make multiple readings and then we use those readings to calculate a mean. Every year after the science exams, social media is full of people who are outraged that they've been assessed on math skills within the science papers. So just to be clear, over the course of all of the GCSE science papers, math skills make up 20% of the marks, and in the physics papers, 30% of the marks are supposed to be for mathematical skills at an appropriate level. So that means if you're taking the higher tier, then the math skills need to be at least GCSE foundation tier, and if you're taking foundation tier for GCSE science, then the math skills have to be at least Key Stage 3 level to count as math skills. So things like adding up numbers just don't count. If you're watching this early enough in advance and you have the specification to hand, then Appendix 9 of the specification gives you a full list of everything that can be assessed. For any of the base units, so things like grams or litres or newtons or volts, there's a version of that unit that's 1,000 times smaller called a millivolt or milliamp or whatever. And then there's a version that's 1,000 times smaller again, which is the micro whatever, and 1,000 times smaller again, which is the nano. And of course it goes the other way as well. So 1,000 times bigger would be kilo, like kilogram or kilometre, and 1,000 times bigger again would be mega, and then giga. and all of these conversions are going to be by factors of 1,000. The only exception is when you're thinking about centimetres, because centimetres aren't a proper scientific unit. But you should still know that there are 100 centimetres in a metre, and that is the only one of these conversions where you're not multiplying or dividing by 1,000. In 2024, like 2023 and 2022, you are going to be given a copy of the physics equation sheet. But remember, this only contains each equation in one format, and you're very likely to still need to rearrange, particularly if you're sitting the higher tier paper. The equation sheet also doesn't tell you what any of the units for these quantities are, so it's a good idea at the very start of your exam to quickly scribble these down. You should know that all forms of energy are measured in joules, and that includes work done, which is just another type of energy. And then mass needs to be measured in kilograms, and this is one of the most likely quantities to be given to you in a different unit. It's very likely that the exam board would give it to you in grams, and then you need to convert kilograms by dividing by 1,000. Then speed is in meters per second, height and also extension are in meters, and gravitational field strength is in newtons per kilogram. Temperature change is in degrees C, and specific heat capacity is in joules per kilogram degrees C. That's one of the harder units to remember, but if you know the other quantities for that equation, then you can work it out because it's just a compound unit. Time always needs to be measured in seconds, and power is in watts. Then we've got charge flow in coulombs, current in amps, potential difference in volts, because of course its other name is voltage, and resistance in ohms. We've already covered all of the quantities in energy is power times time, and energy is charge flow times potential difference, and then we meet the density equation. And this is one of the only examples where the exam board might not use the SI units for a particular quantity. We would normally expect to measure density in kilograms per metre cubed, and therefore have mass in kilograms and volume in metres cubed. But you may also encounter situations where they give you the mass in grams and the volume in centimetres cubed. And then, because density is just a compound unit, you can use those to create a new unit for density, and this is going to be grams per centimetre cubed. Specific latent heat is measured in joules per kilogram, and then mass and energy we've already talked about. The first topic in Physics Paper 1 of AQA GCSE Combined Science is the energy topic. You should know that a system is an object or a group of objects, and a system can store energy, and there are a number of different ways in which it can be stored. It can be stored as a magnetic store, a kinetic store, which means it's a moving object, a thermal store, so a hot object, a gravitational potential store, that's when you've taken an object and you've raised it against the action of a gravitational field, a chemical store, where the energy is stored in the bonds, so that could be a food or a fuel. Elastic potential stores are where an object has been stretched, so say an elastic band or a hair tie or a spring. Electrostatic, that's where we've got the attraction between positive and negative objects. And finally, nuclear stores. It's possible for energy to be transferred between those stores in one of four ways. Energy can be transferred by heating because there's a temperature difference, mechanically by a force, electrically, and finally by radiation. Remember, you can't store energy as light or as sound, but you may have energy being transferred through radiation, and light and sound are types of radiation. Now, conservation of energy is not actually part of this first little topic of energy, but I find it challenging to explain the next bit without mentioning it first, so we're going to do things slightly out of order. We've mentioned that a system is an object or a group of objects, and a closed system is where we have a situation where no matter, so no stuff, and no energy can get in or out. Within a closed system, you can't create energy, you can't destroy energy, you can only transfer it. So if we know how much energy is stored at the start of a scenario, then the amount of energy that's stored at the end must be the same. It might just be stored in different ways. So for instance, you might have started out with a chemical store and you finish with a thermal store, but the total amount of energy will always be the same. Energy is always measured in joules, and you always want to be writing joules with a capital J. And I'd even suggest putting a hat on top of your J, even if you don't normally, just to make that super clear to your examiner. We now have a bunch of different energy stores and the calculations that go with them. In 2024, these are still going to be given to you on the equation sheet, but remember these will only be in one form, so you may still need to rearrange the equation. Also, none of the units for those quantities are listed. A typical question near the start of the higher tier paper or at the end of the foundation tier paper might ask students to calculate how much gravitational potential energy is transferred to an object when it's lifted up. The first thing that you're going to do is to pick the appropriate equation from the equation sheet and write that into your answer space. And then beneath that, you're going to pick the numbers from the question and write them where they correspond to each of the letters. So the mass here is 5 kilograms, the gravitational field strength is 9.8, and the height is 1.5 meters. You need to watch out for the fact that the height has been given in the question in centimetres and you need to convert it. If I multiply all of those numbers together, I get an answer of 73.5, and I'm going to write the units afterwards. It doesn't matter whether you've written your final answer on the answer line that they've given you, or if you've written it earlier in the answer space, provided you haven't contradicted yourself. If you have copied it out, make sure that you don't make any silly transcription errors when you're copying. Our next energy store is a kinetic energy store. This is where we have a moving object. Things to watch out for here are that the squared sign in this equation only refers to the v, so it's only the speed or the velocity that's being squared. It's not the whole lot being put together. Again, a typical question might ask you how much energy has been stored. So you would write out the equation and then write it out with the numbers there in place of the letters. If you don't have the ability to do fractions on your calculator, just use 0.5. It means exactly the same thing as a half. So I write in these numbers and then I do the calculation, I multiply them together and I get an answer of 250 joules, again with a capital letter. Then we're on to elastic potential energy, and again here we've got a squared sign, and again it only refers to the extension. And again, watch out for the fact that extension needs to be in meters, not in centimeters or anything else. It's worth pointing out here that for some questions you may need to calculate one of the other terms in this equation. Say, for instance, here you might need to work out the spring constant. Hopefully you're really confident rearranging equations, but actually even if you're not, you can still answer these questions because, for reasons best known to themselves, when AQA write the mark schemes, they actually prefer you to substitute first and rearrange afterwards. So if I had a question that asked me about the spring constant, which is that k, then what I could do is I could put in all the numbers I know and then solve for k. So say I know that it's storing 4,500 joules of energy. That's going to be equal to half times k, the spring constant that I want to work out, times 3 squared. So if I simplify this through, then I get 4,500 is equal to 4.5k. Well, I don't want 4.5k, I want 1k. So I need to divide by 4.5, and whatever I do to the left side, I do to the right side, and I get an answer of 1,000k. Solving the question like this will still work even without rearranging, and it's still credit worthy. It's actually what the mark scheme does first, rather than rearranging. Next is specific heat capacity, and this comes up in two parts of the specification, so we will come back to it later. Capacity is a concept that you were first introduced to in primary school, looking at how much liquid you could fit in different containers. It just means the maximum amount of something that an object can contain. So then heat capacity is about the maximum amount of energy that a substance will absorb to make it change temperature. And then the word specific tells us that we're referring to 1 kilogram of the substance and we're raising the temperature by 1 degree C. Before we get to the required practical, we have this calculation, and this one can throw people a little bit because it's got some extra symbols in it. The triangle sign is called a delta, and it means change. So this isn't two separate quantities. On the left here, this triangle E means change in energy, and then likewise on the right we have change in temperature. Like density and speed, this calculation is quite a nice one in that the units for the tricky bit, i.e. specific heat capacity, actually tell you what to do with the calculation. If you wanted to calculate specific heat capacity as the subject, you can see that the units for specific heat capacity, which they would probably give you in the question if they were asking you to work it out, are joules divided by kilograms degrees C. So if you have to work out specific heat capacity, you take the joules, the amount of energy, and you divide it by the mass and by the temperature. Watch out for the fact that you do need to have the change in temperature. So you could be given a starting temperature and an ending temperature and need to work out what the difference between those two values are. Also, again, the mass has to be in kilograms, so if it's in grams, divide it by 1,000. The idea of this required practical is that you're given either a metal block or a container of liquid, and you're trying to find out what the specific heat capacity is. In other words, how much energy does it take to heat up 1 kilogram by 1 degree C? Firstly, you're going to have probably a metal block with 2 holes in it, or you might be given a beaker of liquid. You've got a balance because we want to know how much energy it takes to heat up 1 kilogram, and your block might not have a mass of 1 kilogram, so we might need to adjust our calculations to take account of that. You've got some insulation because the experiment only generates accurate data if all of the energy that is given out or transferred by the heater is going into the block or into the liquid. Now, obviously, that's not realistic, and some of it is going to dissipate and go into the surroundings, but we want to minimise those energy losses as far as possible. So you need to insulate the thing you're heating up. We've got a thermometer, so we can identify how much it is heated up by, and realistically, we're not going to heat it up by just 1 degree C, because making small measurements reduces the precision of the final value. So to increase the accuracy of our results, we're going to heat the block up by maybe 10 degrees or 20 degrees, and then divide the amount of energy that has been transferred by 10 or by 20 to take account of that. I've included a pipette here because often that thermometer is not going to make good contact with a metal block. So in order to actually get a proper temperature reading, you add a tiny bit of water in, and that's going to come up to temperature with the block, and then what you're actually doing is taking the temperature of the water. We need some kind of electrical heater in order to heat up the block, and then these last three are for us to calculate the amount of energy that's been transferred. My preferred way of doing this is that you measure the potential difference using the voltmeter, and you measure the current using the ammeter, and you can use those two readings together to calculate the power. Then once you have the power, you can use the stop clock to work out the amount of energy transferred. Alternatively, you could also use a piece of equipment called a joule meter, and that will tell you directly how much energy has been transferred. But joule meters are not mentioned anywhere in the GCSE specification, and so I'm always a little bit nervous about whether the exam board will give you credit for it. So if you can remember how to do the whole thing with voltmeter and ammeter, that's the route I would go down. The final topic in this 6.1.1 energy section is power. Power is the rate at which energy is transferred or the rate at which work is done. In other words, how quickly is energy moved between stores. The more powerful an appliance is, the faster it can do work or transfer energy. A typical early in the higher paper question might just ask you to calculate the power if an appliance like a kettle or a toaster or a washing machine transfers a certain amount of energy in a certain amount of time. Again, here they might be sneaky and give the time in units other than seconds, so just watch out for that. So here in my question in the pink bubble, I would say that the value 2000 must be the energy, and I can tell that because it's got a J after it, and obviously 4 is a time because it's in seconds. So to calculate power, I would do 2000 divided by 4, giving myself an answer of 500 watts. Now you'll notice that to get my answer here, what I've done is a number in joules divided by a number in seconds. So we can also say that a watt is exactly the same thing as a joule per second. And to be honest, our lives would probably be easier if we called it a joule per second, but physicists love to rename units after dead white guys, so that's what we've done here. Then we move on to section 6.1.2, and the first thing we need to know about is efficiency. This is the proportion of energy that has been usefully transferred, and it can be expressed either as a decimal or as a percentage. We've already said that conservation of energy describes how we must have the same amount of energy at the end as at the start. However, some of that energy will be transferred usefully in the way I want, and some of it will be transferred wastefully. So for instance here, my light bulb might transfer 1000 joules of energy, but 100 joules of that energy is transferred as light radiation, and the other 900 joules is transferred by a heating pathway, and that's not what I want it to do. So my light bulb would only be 10% efficient, or we could also report that as it having an efficiency of 0.1. There are two different equations for efficiency, but they're basically exactly the same equation, just one of them is expressed in terms of energy, and one of them is expressed in terms of power. You might get a question that asks you about where the energy ends up when it's been wasted. There will almost always be a transfer to a thermal store in the surroundings, and when the energy has spread out so far that it's not useful anymore and we just can't use it, then we describe that as dissipating. For the higher tier, you should be able to discuss a number of ways in which we can reduce the wasted energy. We can reduce heat loss by insulating something, which is particularly relevant if you're thinking about houses and how they might have loft insulation or double glazing to help them be insulated. We can talk here about the thermal conductivity of a material. So for instance, if you're looking at different kinds of brick, just regular brick versus breeze block, then the higher the thermal conductivity is, the higher the rate of energy transfer by conduction. So in other words, the better conductor something is, the faster it conducts. You can also reduce wasted energy by reducing drag by streamlining. That's particularly relevant if you're thinking about boats or cars or any other kind of vehicle. We can also reduce wasted energy by reducing friction. That could involve using wheels or lubricating moving parts. If those frictional forces aren't reduced, then they can cause energy to be transferred by heating. The final part of the energy topic is about national and global energy resources. You should be able to distinguish between renewable energy resources, which are being generated faster than they're being used, and non-renewable energy resources, or you might be used to calling them finite resources, which are being used faster than they're being generated. All of these energy resources can be used in a variety of ways, including transport and heating, as well as electricity generation. For each energy resource, you should be able to discuss the advantages and disadvantages. You want to think about things like, are they renewable, in which case they're not going to run out? Are they expensive? Do they have carbon dioxide emissions, which you can then link to global warming? Are they reliable? You can't use wind turbines if it's not windy, and you can't use solar panels in the middle of the night. Also, are there geographic restrictions on where you can use them? Then also for nuclear power, you want to think about how you would dispose of the radioactive waste and the risks associated with nuclear accidents. So now we come to the second topic in GCSE physics, which is electricity. The first thing to be aware of is that you need to know all of the different circuit symbols and be able to use these to draw circuits. And of course, it's really important when you draw a circuit that you're using a ruler for your wires and that you're not leaving any gaps in those wires, otherwise you wouldn't have a complete circuit. One symbol to watch out for is when you get your resistor and your fuse. It's really common to see people drawing the lines for the wires and then drawing the resistor on top of it so there's a line going through the middle. But because that would actually then be the symbol for a fuse, it's not correct and you would forfeit the mark. So just really watch out if you need to draw that one. There are a number of different equations in the electricity topic, and bear in mind that even if you're taking your exams in a year when you are given an equation sheet, you might not be told what quantities you're using in the question. So it's really important that you know what all of the units are, so that you can identify that if the question says 200 volts and 0.4 amps, the 200 is the potential difference and the 0.4 is the current. The other thing to be aware of is that for the higher tier in particular, you may get questions where you need to stack more than one equation together to get to a final answer. If you do have a question that asks you to work something out and you can't figure out how to work it out using the information you've got, then see what you can make and try to calculate something, because the chances are it's one of these multi-step calculations and what you've done is the intermediate first step, and that will still get you some credit. You should be familiar with the idea that current is the speed of the flow of charge around a circuit, and potential difference is about how much energy is being transferred by a component. Now, the thing to remember with current is that even though we know now that current is the flow of delocalized electrons, when the idea of electricity was first developed, scientists didn't know about electrons, and so they thought that it was positive particles that were moving. When they started describing electrical circuits, they described current going the wrong way. So even though we now know that it's electrons, we still continue to talk about this, and it's what we call conventional current. Required Practical 15 is about measuring the IV characteristics, in other words, the current and the potential difference of both a wire of different lengths and also resistors that have been placed in series and in parallel. So in each one of these circuits, we're using an ammeter connected in series, otherwise it won't work, to measure the current, and a voltmeter connected in parallel, otherwise it won't work, to measure the potential difference, and then using the calculation R equals V over I to calculate the resistance for each one of these. So essentially what we find is that with a wire, as it gets longer, its resistance gets higher, and then with the resistors in the series and parallel circuits, if you're putting the resistors together in series, then the overall resistance for the circuit can be found by adding up the values of the individual resistances of those resistors. Whereas if we're in parallel, then it's a lot lower, and we're going to look at that in just a second. Then Required Practical 16 is very similar. So here you're asked to investigate the current, which is I, and the potential difference, which is V, for a variety of circuit components. You might be asked to draw a circuit that would allow you to do this, and as we said, it's really important that your ammeter is in series and your voltmeter is in parallel. Just remember that your voltmeter is measuring potential difference, and it can't measure the difference between the two sides of the component if it hasn't been attached on both sides of the component. So here I've got a resistor in the bottom left, which is what I would be currently measuring the current and the potential difference of. So that's what I would swap out for a different kind of component. Having completed that practical, I'd then be able to draw some different IV graphs. Having completed that required practical, you'd be able to draw these three graphs. So these are IV graphs. You've got the current on the y-axis and you've got potential difference on the x-axis. In other words, we're changing potential difference and seeing what happens to the current. So for an ohmic conductor like a wire at constant temperature or the resistor that I had on the previous slide, as we increase the potential difference, we increase the current, and this happens in a linear fashion. In fact, this graph is directly proportional, which means it's a straight line graph and it goes through the origin, 0, 0. In other words, if I double the potential difference, I double the current. A filament lamp looks a little bit different. It's this slightly S-shaped curve, and the reason for that is that it's not at a constant temperature. As the potential difference increases, the wire is getting hot and therefore its resistance is increasing. Even though as you increase potential difference, current is still increasing, it's no longer increasing by the same rate because the resistance is going up. Then finally we have the diode, and there are two important things to note about the graph that you're drawing for this one. The first one is that the diode will only allow current to flow in one direction, so you don't have anything on the graph at all below the x-axis. If you unattach your power source and you reattached it with wires flipped over, no current will flow. Then the second thing to note is that if you only have a very small potential difference, then you still don't get the current flowing. The graph is going to track the x-axis for a little bit before it goes diagonally upwards. Next, you should be familiar with light-dependent resistors and thermistors. Now watch out, because these graphs look similar to the previous ones, but they're not. We no longer have current on the y-axis, instead we have resistance. And what these graphs tell us is that a light-dependent resistor will resist less as the light gets brighter. So that means you could use it to turn on a radio in the morning. As the sun comes up, the resistance goes down, the current starts to flow, and your radio switches on. And then for a thermistor, as the temperature increases, the resistance gets less. So that's opposite to a wire. Next is series and parallel circuits. In a series circuit, there's only one path that the charges can follow, whereas in a parallel circuit, there's a junction where the current splits. So some charges are going to go past one light bulb and some charges are going to go past the other light bulb. For series and parallel circuits, you need to be able to discuss the current, so how quickly the charges are moving, and also the potential difference, which is the amount of energy that's being transferred to these different components. If we think about the series circuit first and current, we've said that current is about how many charges pass a particular point per second. And the image you want to have in your head is that this is like a traffic jam. There are no gaps between charges, and if one charge moves forward, then the ones directly behind it will also move forward, and everything is just going to carry on moving at exactly the same speed. So because there's only one loop and all of the charges are going the same way, they're all going to go at the same speed. So the current anywhere in that series circuit will be exactly the same, regardless of where I put my ammeter. Now the parallel circuit is a little bit different because the charges are still going nose to tail like they're in a traffic jam, but when they get to point A, they're going to split. So if these two branches are identical, if my two light bulbs have just come out of the same packet, then half of the charges will go one way and half of them will go the other way. Now the branches might not be identical, so these could be two different light bulbs with different resistances, or I could have a situation where I've put two light bulbs in one loop of the circuit. But whatever the different currents are, the current for the first branch and the current for the second branch will always add up to be the same as that total current was before the charges split. If we now think about potential difference, that's about how much energy is being transferred. Imagine that as these electrons go past the cell, they're picking up some energy. In the series circuit that I've drawn here, they're going to have to split that energy between the two light bulbs because they're going to go past both of them. So each bulb is only going to get half of the energy that was picked up from the cell. But in the parallel circuit, each charge or each electron is only going to go past one of the light bulbs. So it doesn't need to save half of its energy to give to the other bulb. It's all going to be given up in one go. So whereas for current, it was the same everywhere in the series circuit and it's split in the parallel circuit, for potential difference, it's going to be the other way around. In the series circuit, the potential difference is going to be split between the two components, whereas in the parallel circuit, each component is going to get the full potential difference. And that's why the light bulbs in a parallel circuit are much brighter than those in a series circuit. Finally, if we think about resistance, you should be able to describe that in a series circuit, to work out the total resistance, we're just going to add up the resistance of each individual resistor. So say if I had 3 resistors and they each had a resistance of 2 ohms, then the total resistance would just be 6 ohms. You'd literally just add them together. Whereas in a parallel circuit, the total resistance is less than the resistance of the smallest individual resistor. To actually work out what it would be, we say that 1 divided by the total resistance is going to be 1 divided by each of the individual resistances added together. But basically the most important thing is when you add up all of those together, you're going to find out that the overall resistance is less than that of any individual resistor. The British main supply of electricity is AC, which stands for alternating current. Alternating current is current that repeatedly changes direction. In the case of the main supply, 50 times per second. This helps to maintain power, and it's also important because the transformers that are used in the national grid will only work with an AC supply. In contrast, direct current, which you get in a simple circuit with a cell or a battery, is current that only flows in one direction. As we've said, the frequency of the main supply in the UK is 50 Hz. You should also know that the potential difference is about 230 volts. Be careful here because historically I think it used to be 240 volts, and so that's a number that a lot of people have in their head or that they've heard their parents say, and unfortunately 240 won't get you the marks in the GCSE physics exams. Most appliances are connected to the main supply using a 3-core cable, which attaches to the supply using a 3-pin plug. The outside of the plug is made from rigid insulating plastic to prevent you from getting an electric shock if you're unplugging something that's already switched on. And the pins of the plug are made from an alloy of copper called brass. As you know from chemistry, alloys are harder than pure metals, so this stops the pins from bending when you're plugging something into the wall. You need to know the names, locations, colours and functions of the 3 wires, which can be identified because of the coloured plastic that's put around them. The live wire is the brown wire, and you can remember that it goes on the bottom right because bottom right is BR and so is brown. The live wire carries the alternating potential difference from the main supply. The neutral wire is covered in blue plastic and it sits on the bottom left of the plug. BL for bottom left, BL for blue, and it completes the circuit. It has a potential close to 0. The earth wire has green and yellow stripes, and it's a safety wire to stop the appliance from becoming live if there's an electrical fault where the live wire touches the metal casing of an appliance. The plug has one more safety feature, which is the fuse. So the fuse is just a thin metal wire, and if too much current flows, say if there's an electrical surge, then that wire will melt, and therefore that will break the circuit and just keep everyone safe. Be careful with your language here. It's really common to hear people in everyday life talk about a fuse blowing, and therefore we see students writing that the fuse has blown up or the fuse has exploded. And it's nothing as dramatic as that, and also you won't get a mark for saying that it is. So you want to talk about the fact that the fuse is breaking or the fuse is melting. Most fuses that we see in plugs are either 3 amp fuses or 13 amp fuses. You could be asked what's an appropriate fuse to use, and you'd be given a multiple choice list. So the idea is something that you want to have a fuse that will allow a slightly higher current to flow than what's normal before it melts. So say if the normal current was 11 amps, you would use a 13 amp fuse because that way it's not going to melt unless there's too much current. The national grid is a system of cables and transformers which links power stations where electricity is generated to our domestic customers, things like houses. The transformers are important because they allow this to be a really efficient process. In those central cables that run between pylons, the electricity is travelling with a really high potential difference. And the reason for that is that there are 2 ways that we can get the amount of power that we need to our domestic customers. Firstly, we could have a really high current. That means the electrons are moving really fast, and if that's the case, because they're moving so fast, the wires end up heating up and resisting, and you end up losing a lot of energy to the surroundings. It just dissipates into the atmosphere. So high current doesn't really work for us because it wastes a huge amount of energy and therefore costs a lot of money. The alternative is to have this really high potential difference. But you don't want that high potential difference in the power station and the domestic supply and the houses and the factories, because high potential difference is really dangerous. So what you have is, firstly, between the power station and the cables, a step-up transformer, which increases the potential difference. And then you have this really high potential difference going through the cables, and at the other end, you have a step-down transformer, which is going to reduce the potential difference so that it is safe for consumers again. The third topic in AQA GCSE Physics Paper 1 is the particle model of matter. This starts off with our 3 different states of matter, and you should be able to recognise or draw these simple diagrams to model the differences. Later I've drawn these in a more traditional way with the boxes the same size, but I don't want to give you the impression that the number of particles changes during a state change because that's not accurate. As we go from solid to liquid to gas, as we add more energy, the number of particles stays the same, and so conservation of mass is still a thing. They're just changing how they're interacting with each other and how spread out or close together they are. In the solid, the particles are packed in this regular structure. In the liquid, the particles are still close together and touching. There aren't any gaps that you could push a particle into, and that's why liquids are virtually incompressible, but the particles are no longer in that regular structure. In the gas, the particles are separated by large distances. You should be able to talk about the forces between the particles. In a solid, there are really strong forces holding the particles in place. The forces in a liquid are a bit weaker. The particles maintain contact, so you don't have individual molecules or atoms flying off, but those forces are weaker than they are in a solid. And in the gas, we've got really, really weak forces. You should also be able to talk about the particle movement as well. So in the solid, the particles are still moving, but they're vibrating in fixed positions. So the particles are staying on the spot and they're just vibrating back and forth. In a liquid, the particles are able to pass each other, and in a gas, the particles are constantly randomly moving. In terms of how all of this affects the properties of solids, liquids and gases, it's difficult to change the shape of a solid because you've got these really strong forces and because all the particles are regularly packed together. For a liquid, it can change shape quite easily if you just pour it into a different container, but liquids are virtually incompressible. So in other words, if you put some water in a syringe and you try to squash it, as long as you've blocked the end so it can't come out, you can't squash it because there aren't any gaps for the particles to move into. And then a gas can easily expand to fill a space, and therefore it's easy to compress because it's got these big gaps between particles. You should be able to name all of your state changes. So melting and freezing and boiling and evaporating, which are different to each other. So boiling is where all of the liquid is turning into a gas in one go, and it happens at the boiling point and you're going to see bubbles. So that's like when a kettle boils. Whereas evaporating is where just the particles at the surface are breaking away and becoming vapour or a gas. And so that can happen at a much lower temperature and you're not going to see bubbles. So that's like when a puddle is gradually drying up as it evaporates in the sunshine. And then condensing, which is the opposite of evaporating, and of course sublimating, which is the one that people tend to forget. That's where something turns straight from a solid into a gas. It's very rare, but carbon dioxide does it, and so does camphor wax. You should be aware that all of those state changes are physical changes. In other words, we're not making any new chemicals that weren't there before, and if we reverse the heating or the cooling, then we could go back to the original substance with the original properties. If I took some ice and I melted it and then I boiled it, but then I cooled it back down so it turned back into ice, I'd still have the same ice with the same properties that it had at the start. And in those physical changes, those changes of state, mass is conserved. So if I start out with a kilogram of ice, I'm going to finish with a kilogram of steam, and then from there go back to my kilogram of ice. Thinking about how particles are arranged in solids, liquids and gases leads us nicely onto density. Density is a measure of how much mass is contained within a unit volume of a substance. So if I had a metre cubed of iron and water and chlorine, then because the particles in the chlorine are so much more spread out than in the water or in the iron, within that same volume I'm going to have far fewer particles, and therefore the overall mass of that metre cubed is going to be much lower. This is what we mean when we say that something has low density. The calculation to work out density is mass divided by volume, and this is one of these nice equations where the units give you the equation and vice versa. So the units for density tend to be kilograms per metre cubed. So in order to work out density, we take the mass in kilograms and we divide it by the volume in metres cubed. In the required practical, we need to determine the densities of regular solid objects, irregular solid objects, and liquids. So for each one of those, we need to be able to calculate the mass and also the volume. If we start off with a liquid, you measure the volume of a liquid using a measuring cylinder. So the way to do this is put your empty measuring cylinder on the balance and then tear the balance so that it acts as if the measuring cylinder is not really there and gives you a mass of 0 kilograms. And then you fill up the measuring cylinder with a certain volume of liquid, and the bigger the volume is, the more precise your data will end up being. And then you see what the mass of that measuring cylinder and the liquid are, and then you just read the volume off the measuring cylinder. For a regular object like my cuboid here, you're going to need to measure the length, width and the depth using a ruler, or to be even more precise, you could use the calipers as I've shown here. Then you can work out what the volume is by multiplying the length by the width by the depth. If they give you a cube, then of course all of those are the same as each other. Then to calculate density, we take the mass that we've measured using a balance and divide it by the volume that we've just calculated. Finally, for an irregular object, so something like my keyring here, we're going to need to use this displacement can, or you might also have called it a Eureka can. So you're going to fill this can up with water until water is coming out of the spout, and when water has stopped coming out of the spout, you're ready to measure the volume of your irregular object. You're going to fully submerge that irregular object in the displacement can, and you're going to catch all the water that comes out of the spout in a measuring cylinder. Now the reason that this is going to work is that the volume of water that is displaced will be equal to the volume of the object. So you now have the volume of that object, and you can put that together with a mass that you've measured using a balance to calculate the density of the irregular object. Then we move on to internal energy. The energy that's stored in a system by the particles is called internal energy, and everything has internal energy even if it's not moving right now. The internal energy is made up of two things: the total kinetic energy of the system, in other words the particles that are moving around, and the total potential energy of the system. As you're heating a substance, the energy stored within the system will increase, but that isn't always reflected by an increase in temperature. If we take some ice and we heat it up, we actually see a graph that looks a bit like this, which might come as a bit of a surprise because you might expect the temperature to just go up in one nice straight line. So what's actually going on here? Well, we've got this flat line here where the ice is melting, and another flat line here where the water is boiling. Whenever the substance is going through a state change, the temperature doesn't change. You can almost think of it like the substance can't multitask. Either it can get hotter or it can change state. It can't do both at the same time, assuming it's a pure substance. So the red bits of the graph here represent places where the energy is going into the substance and it's making the particles move faster. So if it's a solid like ice, then the particles are vibrating faster on the spot, and then if it's a liquid like water, the particles are moving faster past each other, and so the temperature is increasing. If I want to know exactly how much energy it's going to take to do this, then we need to know the specific heat capacity, which we met earlier in the energy topic, and that tells us how much energy is needed to raise the temperature of a substance by 1 degree C. Then the green bits of my graph are where the state changes are happening. Here, instead of that energy increasing the kinetic energy of the particles, it's increasing the potential energy of the particles. And so that's where my state change happens. And if I want to know how much energy that's going to take, then I need to know about specific latent heat, which tells me how much energy is needed to change the state of 1 kilogram of a substance. Now, that's not going to be the same amount of energy for melting as it is for boiling, so we have slightly different names. We have the specific latent heat of fusion when a substance is melting, and the specific latent heat of vaporization when it's turning into a gas. Again, this is an equation with quite sensible units, in that energy is measured in joules and mass is measured in kilograms. So therefore, specific latent heat is in joules per kilogram, which is nice and easy to remember. So if I was going to rearrange this equation to make L the subject, it would be the energy divided by the mass. So in other words, joules divided by kilograms, which is just joules per kilogram. You should know that the molecules of a gas are in constant random motion, and the temperature is related to the average kinetic energy of the molecules. In other words, if the temperature is hotter, then the particles are moving faster. Provided we're working at constant temperature, then pressure and volume of gas are inversely proportional. This means if you've got a balloon and you keep it at constant temperature and you squash it so the volume is half of what it was before, then the pressure inside will double. However, as volume decreases, then actually in real life, not just hypothetical physics world, the temperature will increase. The final topic in AQA GCSE Physics Paper 1 is all about atomic structure and radiation. The first part is common content with Chemistry Paper 1, so you've revised all of this quite recently anyway. You need to be able to describe this nuclear model of the atom. So there's a small, dense nucleus containing protons and neutrons, surrounded by electrons, which orbit at fixed distances, which we usually call shells. You should be able to describe the relative masses and relative charges of each of those subatomic particles. It's important wherever you see the word relative that you answer in the form of a number, not just saying positive and negative, but saying +1 for protons and -1 for electrons and 0 for neutrons. You are allowed to say that the mass of an electron is very small because that's what the specification says. Although if you do know a numerical value for it and you want to use that, then that is also fine. In terms of the numbers of these particles, The bottom number for an atom is the atomic number, and that tells you the number of protons, which will be the same as the number of electrons in an atom. And really, in GCSE physics, we're only expecting to meet atoms. We're not expecting them to ask you about ions. That would be more appropriate to come up in your chemistry exams. Then the mass number tells you how many particles there are in the nucleus. So therefore, you can work out the number of neutrons by subtracting the atomic number from the mass number. So for instance, with my lithium atom here, to work out how many neutrons there are, I would do 7 take away 3, which is 4. And you can see in the diagram I've got my 4 green neutrons. You should know that the radius of an atom is about 0.1 nanometers, which can also be expressed as 1 times 10 to the minus 10 meters. And you should also know that only about 1/10,000th of the radius of that atom is the nucleus. We just draw it a lot bigger in diagrams so that we can then pick out the individual protons and neutrons. Now, the reason that all of this atomic structure is relevant is that when we talk about radioactivity, it tends to be different isotopes of elements that we're interested in. Isotopes are atoms of the same element that have the same number of protons, because the number of protons is what defines what element something is, and they have different numbers of neutrons. Now, if you've been revising from something other than an AQA approved textbook, you might also have seen isotopes defined in terms of their atomic number and mass number, but your exam board want you to define it in terms of subatomic particles, and they'll often say in the question, give your answer in terms of particles in the atom. So you need to make sure you're talking about protons and neutrons in your answer, not atomic numbers and mass numbers. Looking at how the model of the atom has changed over time is basically getting across this idea that scientists do experiments, we collect data, and then we update the models in light of that data. So we start out with the British scientist John Dalton, who described atoms as being solid, indivisible, in other words, you can't break them up, spheres. He thought they were like snooker balls, just solid. You couldn't cut them in half because they were just a ball. Next is J.J. Thomson, who discovered the electron and developed the plum pudding model. And this had the negative electrons set in a ball of positive charge to maintain that overall neutrality of the atom. Next comes Ernest Rutherford, who does the alpha scattering experiment, and he is the one scientist where you actually need to know the details of the experiment he did. He took a very thin layer of gold foil and he fired alpha particles at it. So alpha particles are 2 protons and 2 neutrons, so basically the same thing as a helium nucleus. So he fired these alpha particles at the gold foil, and he found that the vast majority of the alpha particles went straight through. And this was evidence that actually the vast majority of the atom was empty space. He also found that a very small proportion of the alpha particles were deflected back, so they bounced back towards him. And this was evidence for 2 things. Firstly, that at the centre of the atom was a small, dense nucleus. And secondly, that that nucleus had a positive charge, because the alpha particles they already knew had a positive charge, and the alpha particles were repelled. And we know that in terms of charges, things with opposite charges attract, and things with like charges repel. So since they already knew that the alpha particle was positive, the nucleus must be positive too. Then Niels Bohr did some calculations and some mathematics, and he said that electrons orbited the nucleus at fixed distances, which we now call shells. And then various people did experiments which corroborated that. Then later there were experiments that led to the idea that the positive charge of the nucleus could be split up into smaller particles which all had the same amount of positive charge, and we called those protons. And then finally, James Chadwick provided the evidence to show that there were also neutrons in the nucleus. You need to know that some atomic nuclei are unstable, and the nucleus then gives out radiation as it's changing to become more stable, and this is a random process called radioactive decay. When we say that it's random, what we mean is that we can't predict exactly which nucleus is going to decay at any one time. You just have to wait and see. Now, as that decay happens, and as the alpha particles or beta particles or gamma rays are given off, we describe the rate at which that decay happens as activity, which is measured in becquerels with a piece of equipment called a Geiger-Müller tube. All of these different kinds of radiation ionize, and what that means is that they turn other atoms into ions by removing their electrons. So you'll know from chemistry that there are ions made when particles lose electrons and when they gain electrons, but in terms of radioactivity and physics, we're always thinking about electrons being lost. The first type of radioactive decay you need to know about is alpha decay. An alpha particle is made of 2 protons and 2 neutrons, so it's just the same thing as a helium nucleus. I start off with my parent nucleus of my unstable isotope, and then as it becomes more stable, an alpha particle breaks off and is released, and what's left behind is called the daughter nucleus. Now this daughter nucleus is going to be a completely different element because it's lost 2 protons, and it's also going to be 4 atomic units lighter because it's lost 2 protons and 2 neutrons. Alpha particles are very ionizing. In other words, they're very good at turning other atoms into ions. They're not very penetrating because they're so big that they're really easily stopped. They have a short range in air for the same reason. They're quite big, so they collide with molecules in the air, and this stops them travelling further. They can be deflected or pushed to the side by an electromagnetic field, and they can also be stopped by a thin layer of paper. Beta decay is also a particle. This time it's a fast-moving electron, and this is often confusing for people because we're talking about the nucleus, so why would there be any electrons in there? The best way to think of this is to imagine that a neutron is made out of a proton with an electron stuck to it. So one of these neutrons is going to turn into a proton, and in the same process it's going to release that fast-moving electron, and that is the beta particle. Again, this element is going to turn into a different element because it's now got an additional proton, and so that makes it a different element. Beta particles are less ionizing, both because they're smaller and also because they've got a slightly lower charge. It's just 1 electron as opposed to 2 protons. However, they're more penetrating because they're smaller, so they can get further before they're stopped. They have a medium range in air, and they're still deflected by an electromagnetic field, but they'll be pushed in the opposite direction to an alpha particle, and they can be stopped by thin aluminium foil. Finally, we have our gamma radiation. Now this is not a particle, it's an electromagnetic wave, and we see it being released at the same time as an alpha particle or a beta particle. But because it's not a particle, when it comes to writing equations, there isn't any difference to the parent nuclei and the daughter nuclei. The gamma ray being released doesn't change what element something is, and it doesn't change the mass of the nucleus either. Gamma rays are even less ionizing than beta particles, and they're even more penetrating. They have a huge range in air. They can move basically infinite distances in a vacuum, and they're not deflected by an EM field, and they can only be stopped by using thick lead. So to summarise what we've said so far, alpha particles can be stopped by paper, the beta particle can go through the paper but will be stopped by the aluminium foil, and then the gamma keeps on going until it meets thick lead. Now, for these nuclear equations for the GCSE AQA exams, you don't actually need to be able to predict what the daughter elements are, but you do need to be able to make the atomic numbers and the mass numbers balance. So for an alpha particle being released, this is relatively straightforward. Radium-219 has a mass of 219, and the alpha particle has a mass of 4. So therefore, the polonium daughter nucleus must have a mass of 215, because the two sides of the equation have to add up to be the same as each other. And then likewise, radium has an atomic number of 86, so if the alpha particle has an atomic number of 2, then the polonium must have an atomic number of 84. The beta particles tend to be where people fall down. The mass is quite straightforward, because the mass of an electron, at least as far as this equation is concerned, is 0, so the mass remains 14. But the really common mistake we see is that people will do 6 minus 1 and end up with 5 instead for the atomic number of nitrogen. And even if you don't have a periodic table in front of you, you're probably aware that that's not right. Now, if you think about this logically, we're trying to make the two sides of the equation balance. So what we're looking for is something take 1 is 6. So the something is going to be 7. If I have a graph, the y-axis could represent activity or count rate or the number of nuclei, and I would handle all of these in exactly the same way. Let's say that my initial activity is 20,000 becquerels. To work out what the half-life is, I'm going to see how long does it take for the activity to fall to 10,000 becquerels. In other words, half of what it was to start with. Then I could read off my x-axis that this was 5 seconds or 12 years or whatever it is. Here I've just marked it with t. Now the interesting thing is that you don't actually have to start where x is 0. You don't have to start at the start of the graph because the rate of change will remain constant. So I could look at how long it takes to get from 10,000 to 5,000, and that would still be the same amount of time. And it would also be the same amount of time to go from 5,000 to 2,500. So if you're given a graph, it's pretty straightforward. You just pick any value from the y-axis and see how long does it take for that number to drop to half of that value. The only advantage of starting where time is 0 is that you then don't need to figure out what the difference is between where you start and where you finish, because where you started is 0. Now the alternative is that they give it to you in terms of numbers. So here I've got a sample where the activity drops from 64,000 becquerels to 4,000 becquerels. What you want to work out is how many times has that number halved, and I would really strongly recommend that you write this out with arrows. We start off with 64,000, which halves to 32,000, which halves to 16,000, which halves to 8,000, which halves to 4,000. Now the problem is that people will then look at this and say this is 5 half-lives, and it's not. Think about how many times has it halved. So you need to count the arrows, not the numbers. Here I can see that this is going to be 4 half-lives. So the 4 half-lives are the 24 days from the question. So 4 half-lives is 24. What's 1 half-life? We divide by 4 and it's 6 days. Finally, we need to talk about hazards, so contamination and irradiation. Radioactive contamination is where you've got unwanted radioactive atoms that have stuck onto something else. So they've made that other object radioactive. And the risk there is because at some point those contaminating atoms are going to undergo radioactive decay, and therefore you'd be exposed to that radiation. Now the exact level of hazard is going to depend both on the half-life and the type of radiation that's being given out. For instance, if you've got some radioactive atoms on you, but they're not going to decay for the next 10,000 years, it doesn't really matter. Whereas if they have a half-life of a few seconds, then you're in big trouble. Now, irradiation is different because it's not the radioactive parent nuclei that are on you or on the object that's been irradiated. What's happened is that you've been exposed to the alpha radiation or beta radiation or gamma radiation that's been given off. This could be hazardous to your health in that it might ionise your DNA and lead to mutation and lead to cancer, but you are not becoming radioactive, and if you move away from that radioactive source, there's no further risk of injury. And we use irradiation really commonly when we're trying to sterilise things, so say irradiating medical equipment to make sure there are no living bacteria on it. So that's it for Physics Paper 1 of AQA Combined Science. I really hope that summary has helped you to feel a bit more confident, and I'm wishing you so much luck for the exams. If you have found this useful, then don't forget to like and subscribe for more GCSE science videos coming soon.